Let us identify what are the forces which are acting during a metal cutting operation. First of all, we shall take the case of a chip. When the chip moves over the top of the tool, it experiences a frictional resistance and a frictional force F is acting. We can also draw a normal to the frictional force N. In addition to that, the chip is also acted by a shear force Fs and a normal to the shear force Fn. The frictional force F is inclined at an angle alpha with the horizontal. What is this alpha? Alpha is the tool rake angle. Since frictional force is acting over the surface or the face of the tool, it is also inclined to an angle equal to the rake angle of the tool. Similarly, the shear force. The shear force is inclined at an angle phi. What is phi? Phi is the shear plane angle. So the shear force is inclined at an angle phi with the horizontal. You can also identify one more force, beta. What is beta? Beta is the friction angle. Next, we shall draw the resultant forces. So R is the resultant force generated due to frictional force F and normal force N. Similarly, R dash is the resultant of shear force Fs and normal to the shear force Fn. This is R dash. Therefore, the vector addition of force F, the frictional force, and the normal gives the resultant R, and the vector addition of the shear force Fs and the normal to the shear force Fn give the resultant R dash. For equilibrium of forces acting on the chip, the resultant R dash and the resultant R should be equal in magnitude, and they should be opposite in direction, and they should be collinear. Collinear means they are acting through the same line. The above mentioned forces which are acting on the chip are not measurable. So they are called non-measurable forces. These forces cannot be directly measured. But there are some forces which are acting on the tool, like cutting force Fc as well as thrust force Ft. These are measurable forces. There are some measuring devices such as tool dynamometer. If dynamometers are used, then we can measure the cutting force and thrust force. If you check the figure, you can identify which is cutting force and which one is thrust force. If you draw the resultant of cutting force and thrust force, that will be given by R double dash. And it is shown in this figure. Here the tool is stationary and the workpiece is moving. That is why the cutting force vector is acting towards the tip of the tool. Similarly, the thrust force is also exerted on the tool by the workpiece. How do you measure the magnitude of non-measurable forces F, N, Fs and Fn? For that, you can use the measurable forces Fc and Ft. If you are measuring the cutting forces and the thrust force, with that you can identify or you can calculate the magnitude of the non-measurable forces F, N, Fs and Fn. For this purpose, we use merchant circle diagram. Let us discuss about the merchant circle diagram. Merchant circle is a graphical method in order to calculate the non-measurable forces acting during machining or metal cutting. The non-measurable forces, frictional force, normal force, shear force and normal to the shear force can be calculated using merchant circle diagram, provided you should be knowing about the magnitude of the measurable forces, cutting force and thrust force or tangential force. Merchant circle diagram is a circle in which all the measurable forces and the non-measurable forces are marked. Let us see the procedure for drawing a merchant circle. For drawing merchant circle diagram, initially you have to draw the 4 quadrants in the plane of paper. Then you have to draw the tool. The tool should be drawn in such a way that the tip of the tool should touch the origin and it should be inclined at an angle alpha, the rake angle, with the y-axis or the vertical axis. It is assumed that you already know the magnitude of the cutting force Sc and the thrust force Ft. So initially we shall mark the cutting force Fc. The cutting force should be marked beginning from the tip of the tool or the origin. So the cutting force Fc is shown here. It is marked along the negative x-axis. The length of the cutting force Fc should be equal to the magnitude. Now we shall mark the thrust force Ft. The thrust force Ft is actually located at the tip of the tool and it is acting along the vertical axis in a downward direction. This thrust force has to be transferred from the current position to the tip of the Fc or the cutting force. Now we shall draw the resultant of cutting force and the thrust force. Let it be R. So the resultant R is shown in the figure. Once the resultant is drawn, you can identify the center of the resultant vector. Let it be this point, and this point forms the center of the merchant circle. Once the center is identified, now we can draw the merchant circle. So this is the merchant circle. The merchant circle is drawn with resultant R as the diameter and the center of the resultant vector as the center of merchant circle. Once the merchant circle is drawn, now we can mark the non-measurable forces. First of all, we shall mark the frictional force. The frictional force is acting along the face of the tool. We shall transfer this force to the tip of the tool. Okay, now the frictional force is marked. The frictional force is inclined at an angle alpha with the vertical. The frictional force should start from the tip of the tool and it should end on the circumference of the circle. Now we shall mark the normal to the frictional force. The normal to the frictional force should be marked in such a way that it should start from the frictional force tip and it should end on the tip of the resultant. Therefore, the frictional force Ff and the normal force are marked with its resultant coinciding with the resultant of cutting force and the thrust force. If you want to measure the magnitude of frictional force or the magnitude of normal to the frictional force, you can directly measure it from the merchant circle. Now, the magnitude of two non-measurable forces, the frictional force and the normal to the frictional force, are obtained from merchant circle. Now we have to calculate the magnitude of shear force and the normal to the shear force. For that, we have to initially mark the shear plane. How can you identify the shear plane? For this, you have to draw a line parallel to the x-axis as shown. This line should be located at a height T0 above the x-axis. What is T0? T0 equal to uncut chip thickness. Now we shall draw another line parallel to the face of the tool as shown here. This line should be located at a distance Tc from the face of the tool. What is Tc? Tc is the thickness of the chip. So you have drawn two lines. One is parallel to x-axis, which is at a height T0 or the uncut chip thickness. Similarly, you have also drawn another line parallel to the face of the tool, which is at a distance Tc, the thickness of the chip. You can find the intersection of these two lines by the dot as shown in here. The red dot is the intersection of the two lines. Now we can draw the shear plane through this point. So the shear plane is marked. Through the shear plane, you can draw the shear force vector. The shear force vector should start from the origin and it should pass through the shear plane and it should end on the circumference of the merchant circle. Now the shear force is marked. Next, we have to draw the normal to the shear force. We can also draw the normal to the shear force from the tip of the shear force vector. The normal to the shear force Fn is marked. This completes the merchant's circle. Now you can measure the magnitude of shear force Fs and the normal to the shear force Fn. So you started drawing the merchant circle with the measurable forces Fc and Ft. Now you are able to obtain all non-measurable forces. You can also mark the shear plane angle phi as well as the friction angle tau as shown in this figure. Sometimes you may be able to obtain the shear plane angle phi directly from the photograph of the cutting operation. In that case, it is easy to draw the shear plane. Here you can directly draw the shear plane with an angle of inclination phi. This is all about the merchant circle. The following are the assumptions for drawing the merchant circle diagram. You can go through these points. Let us go into more details of the merchant circle diagram. A merchant circle diagram is given here. The notations used here are little different from the previous one. Here you can find the rake angle alpha, the cutting force Fc, the thrust force Ft, and phi is the shear plane angle. And what is lambda? Lambda is the friction angle. And F is the frictional force, N is the normal to the frictional force, and R is the resultant of all the three triangles, and it forms the diameter of the merchant circle. Certain equations are derived from the merchant circle in order to find the magnitude of non-measurable forces. The non-measurable forces such as F, frictional force, the normal to frictional force, similarly the shear force and the normal to shear force. Certain equations are derived for finding the magnitude of these forces from the merchant circle. If you go through these equations, you can find that these equations are written in terms of Fc, the cutting force, Ft, the thrust force, alpha, the rake angle of the tool, and phi, the shear plane angle. We know that Fc and Ft are known forces. We can measure it using the tool dynamometer. Alpha is the rake angle of the tool, which can also be directly measured from the tool. The shear plane angle phi can also be measured from the photograph of the cutting operation. You can either use the graphical method called the merchant circle in order to find the magnitude of unknown forces, or you can also find the magnitude of unknown forces by applying these equations directly. Next is the coefficient of friction mu. Mu is given by the ratio of frictional force and its normal. So frictional force by the normal to frictional force is given as the coefficient of friction. For F and N, you can directly supply the above two equations. These two equations you can directly supply for F and N. Finally simplifying, you will get Fc tan alpha plus Ft divided by Fc minus Ft tan alpha is equal to the coefficient of friction. Once the coefficient of friction is known, you can find the value of friction angle lambda. Friction angle lambda is given by tan inverse of the coefficient of friction. These two equations shows that the measurable forces are written as functions of non-measurable forces. Okay, there is an equation for finding the shear plane angle phi. Tan phi is given by r cos alpha divided by 1 minus r sin alpha. You can by heart these equations where r is chip thickness ratio, which is given by the uncut chip thickness divided by chip thickness after cut, that is T by Tc. You know the alpha is the rake angle of the tool. Suppose B is equal to the width of uncut chip, then area of cross section of the uncut chip is given by B into T, where T is the thickness of uncut chip. If you multiply the thickness of uncut chip with the width of uncut chip, you will get the area of cross section of uncut chip. If you know the area of cross section of uncut chip, you can divide it by sine of the shear plane angle. This will give the shear plane area.